Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3, 2026, exactly 1 week ago. It introduces RDT2, a robotic foundation model built on a massive dataset of over 10,000 hours, capable of zero-shot generalization to unseen objects, scenes, and even entirely different robot platforms. The paper is titled RDT2, Exploring the Scaling Limit of UMI Data Towards Zero-Shot Cross-Embodiment Generalization. And, as we'll see later, the results on dynamic tasks like table tennis are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, to build that massive dataset, the authors first had to solve the data collection bottleneck. Figure 1 illustrates their solution, the redesigned Universal Manipulation Interface, or UMI. Panel A shows the handheld unit used by humans to record demonstrations, which now includes an infrared tracker for precise positioning. Once the data is collected, the exact same camera and gripper setup mounts onto a robot arm, as shown in Panel B. This consistency is crucial because, as Panel C depicts, it allows the learned policy to transfer zero-shot across completely different robot frames. So, while Figure 1 showed the concept, Table 1 details exactly how the hardware was upgraded to handle scale. First, for fabrication, they switched from standard 3D printing to CNC machining with nylon and glass fiber, which provides the stiffness needed for long-term collection. Next, they replaced the SLAM tracking system with infrared light. This is a major change because it improves robustness on textureless or transparent backgrounds where visual tracking often fails. Finally, the end effector now uses a linkage gripper, which allows for better dexterity in cluttered environments. With the data collection hardware sorted, Figure 2 outlines the 3-stage training pipeline used to build the model. In the first stage on the left, they pre-train a 7 billion parameter vision language backbone using discrete action tokens, which aligns high-level semantic reasoning with low-level robot commands. Then, moving to the middle panel, Stage 2 introduces a dedicated action expert. Here, the large backbone is frozen, and a smaller diffusion model learns to generate smooth, continuous actions by attending to the backbone's features. Finally, on the right, Stage 3 distills that diffusion process into a single-step generator, which drastically boosts inference speed for real-time control. So, having set up the pipeline, Figure 3 reveals how well it actually works in a zero-shot setting. This chart compares success rates across 5 task types, ranging from simple picking to more complex wiping and shaking actions. The red bars represent the model, using only the discrete vector quantization from Stage 1, while the blue bars show the performance with the continuous flow matching added in Stage 2. You'll notice that for dynamic tasks like wiping and shaking, the flow matching variant typically leads, achieving success rates up to 52%. This confirms that adding the continuous action expert helps the model handle finer motor skills better than the discrete policy alone. Well, success rates are only half the battle. Real-world robots also need to think fast. Figure 7 compares the inference frequency of RDT2 against state-of-the-art baselines. On the far left, you see that models like Pi0 Fast and the basic VQ variant are quite slow, running under 3 Hz. In contrast, the green bar on the right shows the RDT2 ultra-fast model hitting 23 Hz. This is remarkable because, despite being a larger 7 billion parameter model, it outpaces the smaller 3 billion parameter Pi 0.5 shown in the middle. Alright, while Figure 7 focused on inference speed, Figure 5 justifies the model's massive scale by establishing a scaling law for robotics. The left panel plots training loss against the number of tokens seen. Notice how the red curve, representing the largest 7 billion parameter model, achieves the lowest loss much faster than the smaller models shown in blue. This benefit is reinforced in the right panel, where increasing model parameters consistently drives down loss, especially when trained on the full dataset as indicated by the dark purple lines at the bottom. So, having established the scaling benefits, Table 2 demonstrates how that translates to real-world fine-tuning performance. This table compares RDT2 against the Pi0 baselines on 5 challenging tasks, ranging from cloth folding to table tennis. Looking at the cloth folding section at the top, RDT2 achieves a 77% success rate, which is more than double the 36% of the next best model. Crucially, in the unseen object row just below that, it maintains 51% success where others drop to just 15%. Further down, For dynamic tasks like table tennis, it hits 88% of balls at standard speed, whereas the fast variant of Pi 0 couldn't even attempt the task. Wrapping up, 2 takeaways stand out. Scaling embodiment agnostic data is the key to generalist robots, and bridging discrete reasoning with continuous control effectively solves the precision gap. This suggests that scaling laws apply just as strongly to physical action as they do to text. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.